Hello, welcome. You guys having a great build? Yeah, excellent. I'm Jeffrey Snover, a technical fellow at Microsoft, and it is my great pleasure to introduce Scott Havens. Scott works at jet.com, and it's one of my things I like most about Build is now we're starting to bring in people from the industry, and it's not just Microsoft talking to you about our technology, which of course we love, but you have industry experts who've been taking this technology to solve real-world problems, so they can tell you where it works and where it doesn't. So Scott works at jet.com and Walmart Labs. Okay, he's focused in on a bunch of the data-intensive systems. And interesting note, jet.com is one of the largest, if not the largest, employer of functional programmers. Okay, so if you got anybody, if you or your friends are want to spend your life coding F#, this is the guy you want to talk to. Now, Walmart in 2016 took a look at this digital transformation and decided that the best way, that if they were not on that bus, they were going to be run over by that bus. And they just concluded that the best way for them, the best and fastest way for them to get on that bus was to acquire jet.com. And so now Scott and his team are taking the techniques that they brought to jet.com and applying it to the world's largest retailer. So let's give a big welcome to Scott Havens.
Thank you for that wonderful introduction, Jeffrey. So you heard a little bit about jet.com. You know that we are a mass market e-commerce company, and we've been dealing with scale from our earliest days. And in 2016, we were purchased by Walmart. After purchase, for a few months, we had started some early integrations of systems, make sure that our catalogs can kind of talk to each other, make sure our order processing systems can kind of talk to each other, but never any advanced full-fledged integration where we're unifying the systems. There's always going to be politics at a large company, especially when two companies are being merged together. But one of the reasons that Walmart had bought Jet in the first place is because our tech looked cool. It looked transformative. But not everyone goes into that scenario being convinced that our techniques are going to be providing real benefits. Well, it wasn't long before we were fortunate enough to get the chance to demonstrate these benefits. And by fortunate, I mean disaster struck. In the middle of March last year, a little bit after 3:30 a.m., I got paged. I woke up, hopped on our bridge for pager duty in case anyone wanted to talk about the problem, and started looking into it. And almost immediately, I was joined by coworkers from several other teams. It turned out our production Kafka cluster was down. Kafka, for us, is the primary method of communication among all of our back-end services. We try to stick with asynchronous messaging whenever possible, and Kafka's worked really well for us for that. However, in this case, it was not working. Everything went to a dead stop. Before long, we realized it wasn't just down, but dead. Every single message in flight in Kafka was gone. Customer orders, replenishment requests, catalog changes, inventory updates, warehouse replenishment notifications, pricing updates, every single one was gone. We were going to have to rebuild the cluster from the ground up. Now, this could have been catastrophic. This could have been the end of the Grand Jet experiment, enough to convince our new Walmart compatriots that Jet's technical tenets sound good on paper, but don't work in a real enterprise compared to tried and true systems. So what happened with that? Well, you're going to have to wait to the end to find out. First, let's talk about those tenets, those principles that have guided us. What does Jet do differently? There were several idiomatic practices that when I was first interviewing at Jet, the parts that made me really excited were that they were so big into functional programming and F# in particular. I've done a lot of functional programming style in C# at other organizations, but I was really excited to work with a language that made functional first, made doing the right thing easier. There have been a lot of spikes in early systems done before I got there that showed that it looks like there could be a lot of benefits from adopting F# as our language of choice. Another big thing, one of the early principles I learned joining Jet was that we treat microservices as stream processors, and we then make everything a microservice. That works really well with the functional paradigm. Then the third thing that I had tried at other places but didn't have a real good grasp on the exact right way to do it was event sourcing. I'll talk more about all three of these things later. The benefits, as we'll talk about a little bit later, include resiliency, the fact that it's really easy to add features, the fact that it makes systems really scalable, makes systems really testable, and it gives you a time machine. That's not a typo. That is not me misspeaking. You actually do get a time machine with this. We'll talk about what that means in a little bit. So now that we've gone through all these concepts, let's talk about them in a real-world system. First, an aside about naming systems. In the early days at Jet, we were spinning up an e-commerce company, which meant a lot of new systems and a lot of new teams in a short period of time. Having a theme made it fun, made it easier to come up with new names. And the first ones were the obvious ones, Batman and Superman. 2 years into building systems and teams, a lot of the big names were taken. We were in the early stages of planning out a new system, and I tried to think of a name of a superhero who wasn't yet popular enough to be chosen, but who might have some clout a couple years down the line. So, ladies and gentlemen, for today's case study, allow me to introduce Panther. Couldn't get the rights from Marvel for any of the official Black Panther media, but I think this is a better option. Black Panther is the inventory tracking and reservation management system. On the supply side, it aggregates and tracks all sources of inventory, not just from Jet and Walmart-owned warehouses, but from all partner merchants and all of their warehouses worldwide. Then on the demand side, it acts as the source of truth for reservations against available inventory. When a customer is checking out, the contents of their cart get reserved. If the inventory is not available at that point, the reservation fails, and either the items must be resourced from a different location or a different merchant, or the customer needs to be given the option to choose a different item. Between those two, our primary goals are to maximize on-site availability while minimizing reject rates due to lack of inventory. Our secondary goals are to improve the customer experience by reserving inventory earlier in the order pipeline, to enhance insights for the marketing and operations teams by providing more historical data and better analytics. And we wanted to unify the inventory management responsibilities that are typically spread across multiple systems. Of course, with all of these business goals, our solution had a lot of non-functional goals as well, like high availability, geo replication, and really fast performance backed up by SLAs. Now, geo-replication and performance are a fun problem in this domain because actions taken by any customer in the world can affect the validity of any subsequent attempted actions by any other customer. To get the lowest latency, we want to serve our East Coast customers data from an East Coast data center and our West Coast customers from a West Coast data center. But we don't want one customer in each region to try to purchase the last baseball sitting in our Kansas City warehouse and both be told that they successfully ordered it. Now, lots of you will recognize this as a fundamental problem of distributed systems. You can get perfect consistency, guaranteeing that the data is exactly the same no matter which node you check, which is really good for making sure that you don't lose anything if an entire region falls into the ocean. Or you can get really good uptime and latency using all your nodes to make sure that a customer can hit the site and that it's responsive, but you can't get both at the same time. There's always a trade-off, a spectrum from consistency to availability. This also informs our design choices, as it must in many domains that might have people from different geographic regions interacting. So let's jump into how we built Panther and how it solves these problems. Panther uses what we consider at Jet to be our canonical building block for how to build the data-intensive systems. We call this the command processor pattern. Some of you may recognize this from elsewhere, where we have a stream of commands that come in that are processed by a process command microservice. The command microservice, and I'll go into more detail on all of these stages in just a second, but as a quick overview, the command microservice will pull in the state, whatever state is relevant, to execute the command against that state. This execution will produce an event as output. The event gets written into its appropriate event stream. And then those events are emitted via Kafka, via event hubs, or any other mechanism that you may choose, down to all other downstream systems. The state itself is built up over time with a snapshot service. You don't want to have a stream that goes on forever and try to rebuild the state from that every time. So instead, you cache the most recent state of the stream using an asynchronous service back into a snapshot data store that can be used in real time with lower latencies. And we'll go into details in all of these in a moment. So first, let's dig into the first part. What does it mean to execute a command and produce an event? For us, it's a several-stage process. One, you ingest the message. This could be coming in from Kafka, it could be coming in over HTTP, coming over some kind of queue. Any of these would work. It could be in JSON format or protobuf, Avro Thrift. Any of those can work as well. We've tried a few different inputs and a few different protocols at Jet, and we've been using just native JSON zipped and starting to move toward protobuf, and we're very heavy users of Kafka for our asynchronous messaging and HTTP direct connectivity when it has to be synchronous. The next step is that we'll deserialize that payload of the message into a strongly typed command. Now in F#, we deserialize all of these into F# record types. Here's an example here and the kind of data that we would normally see in a command. They're usually not very heavy. It has an ID that can be used for idempotence, whatever the relevant data is to identify what the context is. In this case, it'd be an order and a SKU or item identifier. At which fulfillment node or warehouse we want to be reserving it, how much you want to reserve, and then a little bit of metadata, who's doing it and at what time. Now the commands are messages that express intent to change state. They're named with imperative verbs and then usually followed by a direct object. They could be update inventory, reserve inventory, cancel reservation, or ship order would be some that you might see in this domain. Now in F#, we have a really nice property of being able to describe the entire set of commands that could possibly be processed by a particular command processor via discriminated unions. And if you're not familiar with discriminated unions, in languages that have algebraic data types like F#, you can do a match against any particular item in a discriminated union, kind of like a switch. Some languages call it a choice type or a tagged union. Here it's a discriminated union. It works well for message handling when you have a set of known message types. Here are a couple examples to give you an idea of what a discriminated union might look like if you're not familiar with it. For colors, you would have 3 options, red, green, and blue. And these are untyped, which looks like an enum. But you can also add types to your discriminated unions. Instead of just being a list of string or numbers, they can be full types themselves or tuples of types. So we have an example on the lower half where you might have a union of shapes, or a rectangle is defined by its height and its width, whereas a circle would be defined just as its radius. So this is what it looks like when you have a set of commands in a discriminated union. You have the different types in the discriminated union, each of which is referring to an entire standalone type of its own. I showed you the reserve inventory command earlier, and you'd have similar ones for update, cancel, ship, and however many other commands you'd like. A few years ago, when I was working entirely in C#, I tried something like this a couple different ways with typecasting. I would have a base message class, and then messages would inherit from it. Or in another, I tried a message of type T. In both, I did typecasting with a lot of switch statements. What makes this model really nice is that it's an exhaustive set. the compiler knows that you need to handle every single case. If I add a new command to this list and I don't add the code to handle this case in every place an item from the command discriminated union is used, the compiler will tell me, and I will know that I need to go in and put in the code that I need to have there. So once we've completely deserialized the strongly typed command, we move on to step 3, where we retrieve the state from the database. For inventory commands, just as an example for this domain, the appropriate identifier is usually the SKU ID plus the FN ID, or the warehouse ID where that's being stored. So it will retrieve at that point, say, the current inventory or the available inventory counts for that SKU at that warehouse. Also, and this will be important in a moment, it retrieves a logical clock for that state, a monotonically increasing integer that identifies the last update. That clock is called a sequence number. If there have been a million changes to this inventory, the sequence number would be 1 million. Raw inventory counts aren't the only state in our domain. Some commands like ship order expect a reservation probably exists as well and will include the order ID to retrieve that matching reservation state in addition to just the SKU availability state. So you can get a lot as complex as you want with the amount of state that you need to retrieve. So once you have the command that's describing your intent and the current state you want to change, you execute the command against the state. Executing the command itself does not change the state, but it executes the business logic that usually consists of validation rules. In some cases, like update inventory, the command is coming straight from the merchant or it's straight from the warehouse management service. They're the source of truth, so the validation is trivial. You just reset the quantity at that point. But some other commands may have some real validation rules. Reserve inventory would be a great example, but still simple enough to talk about here. Is the quantity being reserved less than or equal to the quantity available to sell? Great. In that case, it worked. If not, then it failed. So if executing the command itself doesn't change the state, what does it do? It emits an event as output. An event indicates that something has happened. It usually flips the syntax of the command that has triggered it with a past tense of the verb. Instead of update inventory, we now have inventory updated. Instead of reserve inventory, we have inventory reserved, and so on. And failures are events too. If instead of getting an inventory reserved, if the quantity wasn't enough, you might get a reserve inventory failed event as output. The idea is that the events cover every single potential domain output from the execution of the command. So with that output event in hand, you commit the event to the event stream. It's only provisional until it's committed. You can attempt to write the new event to the stream at the next sequence number. If the write is successful with no conflicts, then the event at that point has officially happened. If the write attempt fails due to a conflicting write, say another writer has already written an event with that particular sequence number, then this event is invalidated. We know that the state has changed or potentially has changed, so we have to retrieve the changed state and re-execute the original command. Now, it should be noted that this model of processing commands or of processing a stream of commands lends itself extremely well to a functional style of coding. You're starting with your immutable inputs, your command, which is just an immutable message, and your current state, which is also immutable. You run it through a chain of stateless functions. You decode your retrieval of state, your execution of command, your creation of an event, and then you write a new immutable output to your data store. This works great in a functional style. So now we have an event stream stored somewhere. How do we build the current state from that? Well, it turns out this is also really well suited for functional programming. There are 3 things we have to do. We have to define a 0 state. In our domain, this is really easy. It's just an unknown SKU at an unknown warehouse with 0 on hand. That's what we use when we're starting from scratch in the event stream. We need an apply function that takes a state and an arbitrary event as parameters and produces a new state as output. This is where the meat of the business logic usually is in most domains, and that's the case here. After inventory updated event, the on-hand, the state, will be reset to whatever the merchant told us in that event. The count of completed, in other words, shipped reservations we were keeping around for accounting purposes can be reset to 0. We don't need to worry about those anymore. We have a new canonical count. After inventory reserved, the on-hand would stay the same. The total reserved would increase by some amount, and thus the available to sell will be decremented by that same amount. Finally, we have a fold function that takes the apply function we just defined, a state, and a sequence of events to apply. So we can start from scratch, have an arbitrary sequence of events, and keep folding in those events until we get to the current state. And this is exactly what Snapshot Event Stream does. It reads in a batch of just committed events from the change feed, retrieves the latest snapshot from the snapshot data store, applies the entire batch of events, and overwrites the old snapshot with the newly updated one. That happens in our domain. It's a little more tricky since we have multiple ways of snapshotting a stream. It would be the latest quantities along with the latest state of each individual reservation in that stream, but the idea is the same. Now, while I've described doing this after the fact, after the event is written in Snapshot Event Stream, it's important to know you could also do this in the execute command microservice if the snapshots are not up to date, especially if there are a lot of events coming in or a lot of commands coming in that are producing a lot of events. Maybe the asynchronous snapshotter isn't always keeping up with every last event in time for the next one. So the command executor can not just get the latest snapshot from the state, but can get the latest snapshot and any events written since that snapshot. The snapshot has a sequence number associated with it, so if the snapshot's still only at 1 million, even though the stream has progressed by a few events, you can query the event store for all events that are greater than 1 million, apply those 3 resulting events to the snapshot in memory, and continue on your merry way. Now, we've learned a lot in our practices of what makes good event stream design, and we've made a lot of mistakes along the way as well. Since event streams are defined as every event that happens to an aggregate over time in a linearized or strictly ordered fashion, this is a constraint that has a lot of real-world practical implications as well. Different event streams don't always have a global ordering. There's nothing that forces a given event from stream A to have happened before or after any given event from stream B. You may know every single change that's happened to the item in warehouse over here, and you may know every change from the warehouse over here, but you have no idea which came first. We want to define an aggregate, a stream, as narrowly as possible because imposing order has a cost, usually in the form of a minimum amount of time it takes per event, which inhibits scaling throughput on a given stream. We started in our particular domain with defining all events that happened to a particular item because it was convenient. We eventually realized that item at a given warehouse is more appropriate. We were conflating independent events in the same stream. A reservation on a box of tissues in warehouse A in New Jersey has 0 impact on whether we should be permitted to reserve a similar box of tissues in a different warehouse in California. We found that then we could achieve higher maximum throughput by splitting. If you have your item spread evenly across 10 warehouses by using 10 different SKU fulfillment node streams instead of just one SKU stream, we can get 10 times the throughput because of that. Now, because streams are independent, or once you have streams that are independent, it's good to note that the number of streams should be able to grow arbitrarily and distribute easily. It makes it a really good fit for storage systems that happen to be partitioned and achieve their scalability through partitioning. So given that idea of what the core flow of data-intensive microservices or set of microservices at Jet looks like, how does that fit into a larger architecture? In the middle, you'll see that same core flow with a lot of extra stuff on the outside. And that's not a mistake. You'll see this pattern over and over when you look at services at Jet. The center core flow with the command processor, event streams that are then emitted as events. And what you'll see that's really different in the architecture is different inputs and different outputs. In this case, for our domain, we have both asynchronous inputs and we have synchronous inputs. The asynchronous ones on the bottom, as I mentioned earlier, usually come in through Kafka. Our inventory updates, our order updates, these in large part are coming from external merchants where there might be some kind of delay, maybe just a few milliseconds, but it works really well in an asynchronous fashion. On the top side coming in, we have the customers who are actually on the website checking out as we speak. We want to be able to give them an immediate response every time so they can know whether that item has actually been reserved or not. We don't want to make them wait any longer than would be expected. So instead of going in through Kafka, we send those commands in over HTTP. We have two different command processors, one hosted in HTTP versus a Kafka reader, but the domain logic that's within them is exactly the same. They both work the same way and write events to the same data store. Now, on the other end, the events getting emitted from your system may not, everyone who's listening to these events may not care about every single event that you have. They might need some kind of transform into whatever format they desire, or they might want to filter it down to just the events that they want. So you'll see that in the upper right-hand corner. We have the sellable inventory in a raw form that's being emitted out as an event over Kafka. But for our different marts, whether we're actually selling an item on Walmart.com or on Jet.com, on Hayneedle or any of our other marts, they may not care about the inventory at every warehouse or every single SKU. Hayneedle, which is a site that is selling primarily home goods, probably isn't going to be caring about our grocery items that we're also tracking. So we filter it out in that way. It also gives us a chance to put in any kind of buffers or any other kind of Mart-specific logic for any particular downstream consumer. But the key is that having those filters and those maps don't change the core processing flow. Now, what were we using, or how do we write the events to a data store? Originally, and some of the systems at Jet still do this, we were using an open source product called Event Store. It has a great API for streaming events and being able to read back a stream of events. It's very clean, and it turned out it does not scale to the performance and geo-replicated characteristics that we want. So instead, we ended up with Cosmos DB. Most of you at this point have at least a cursory knowledge of what Cosmos DB is. We found it by far the best choice for designing an event store on top of it compared to a lot of the other competitors that we've gotten to look at. And we've been lucky enough to work with the Cosmos DB team on the feature design to help make an even better event store. So we use it in several different ways. One is for the event stream storage itself. We've written an API that looks very similar to the event store API with which we were familiar before, that reads and writes JSON events. The storage is partitioned by a stream ID, and each event is stored as a new document. Within the name of that document, we have an incrementing counter that matches to the sequence number mentioned earlier. We take advantage of the tunable consistency models that Cosmos DB offers. The next to loosest is called consistent prefix consistency. Without going into what technically that means one very important guarantee that it provides is that you can't accidentally create two documents with the same ID. The second writer will get an exception, and this is how we implement optimistic concurrency. Now, this is something that a lot of the competitors can't provide at the scale that we're talking. One data store that we looked into heavily in building the system was Cassandra. Unfortunately, Cassandra, in a geo-replicated environment, if you have something on the East Coast and the West Coast, because it is multi-master and only multi-master, can't provide us the consistent prefix model without going into full so-called lightweight transactions. And unfortunately, what that means from a performance perspective is that if you have an East Coast and a West Coast data center trying to maintain a consistent prefix, you're doing four hops for the consistency model called Paxos, which reduces the throughput down to about 4 events per second per event stream, which just isn't enough scale for what we're talking about. We also use Cosmos DB as snapshot storage. As a document database, it's well suited for low latency, high throughput reads and writes. We get, in practice, 1 millisecond reads, that's including the network, and the writes are usually in the 5 to 6 millisecond range for us. The snapshots that we write, the roll-up of the entire state, is fully indexed and queryable with a SQL variant language. So for a given stream, we store both the roll-up of the item warehouse state, for instance, the on-hand quantities, the available to sell quantities, and all of the reservations for items as snapshots. The third feature that we found to be just a killer feature in Cosmos DB is the change feed. We're also lucky enough to work closely with them on the design of this so that it would work really well for an event sourcing mechanism. Every single change that gets written to the data store, once committed, is immediately available through the change feed. Now, we modeled this interface after Kafka consumers. So some number of consumers divide the database partitions among themselves, rebalancing as consumers drop out or some more spin up. You can regularly checkpoint your progress, and those checkpoints are then geo-replicated along with the data store. And you can start the consumers from the latest point in time, from the beginning of time, or from an arbitrary date time in between. What makes change feeds so nice is that it eliminates dual writes, which we found in practice to be one of the biggest causes of divergent state in non-resilient systems when you're talking about a distributed system. The common pattern where you need to write to a database and notify an external system that something has changed, or you are writing to two databases, or anytime you're writing multiple times from the same thread and hoping that all of them work, or trying to coordinate it with distributed transactions, just doesn't work very well. You will get divergence over time. With a change feed-based design, everyone who needs the data will get it eventually. There's no such thing as undetected divergent state, only state that hasn't yet converged, with a constantly known measurable time to convergence. Now, this is another thing that when looking at competitors, we couldn't find another one that did this well. To use Cassandra again as an example, they did finally introduce a change data capture output, which works similarly, at least on the surface. But it is a limited amount of time and storage. If the change data capture is enabled, but the consumer from Cassandra isn't live and keeping up, the pre-configured buffer will fill up and writes to that table will stop. The intent is for a single consumer to read and then delete the log contents, but you can't start consuming to an arbitrary date time and pick up from there, especially not from the beginning of time. If you really want multiple consumers, you need to coordinate and have only one purging completed data. It's a good start, but it is just not as full-featured as the Cosmos DB change feed. And it has a lot of other features of note. As you probably know, it is fully geo-replicated with controllable failover and a 5.9 uptime SLA. The TTLs are assignable on a per document, so you can automatically delete old records from the event store if you don't need them anymore. We found this to be really helpful in dealing with the large amounts of data that inherently get stored in an event store. If a particular event has been stored off to a cheaper bulk cool storage location, then we may not need it in the hot event store anymore, and we can let it expire. And Cosmos DB gives us really easy scaling, including an API so we can algorithmically control auto-scaling. This is something that we've started introducing where we either based on the number of request units being used in Cosmos or on some business level metrics such as how far behind we are in processing orders, we can scale up or scale down our Cosmos collection. So this design, as I promised earlier, does have a lot of benefits. The first one I want to talk about is resiliency. And just to make sure we're all on the same page, what is resiliency? To me, it means when a system stays functional with little or no customer impact in case of an outage, or even just a partial outage. It means that recovering from these outages is trivial. And it means that any errors that you get are either trivially corrected yourself or self-correcting. So what are some types of problems that this architecture helps us solve in resiliency, in the domain of resiliency? One is when bugs in code produce our own bad state. If we find a bug, we can fix the bug, redeploy our code, roll back to whatever the command stream to whatever point in time came before the bug and replay everything up to that point to fix the error. We might have out-of-order reservation workflow events. We have a bunch of different sources in the architecture diagram. It could have been from any number of third-party merchants, order management systems, third-party APIs, warehouses, all of these different sources of data, they are not synchronized. They may try to be, and they may be most of the time, but there's no guarantee that they will be all the time. So commands and events may get out of order. So how do we deal with it? Well, we've adopted a lot of learnings from what are called CRDTs, conflict-free replicated data types, and other lattice-based structures, where if we adopt a certain number or a certain set of principles in our domain design, it gives us a lot of flexibility in how we're processing events in order or out of order. We need to make sure that our events are idempotent. If we process an event multiple times, it shouldn't matter. We should still end up in the same state. We need to make sure that our events are commutative. If you process event A and then event B, and then swap and process event B before event A, you should still end up in the same end state. Now, you can do that by adopting some principles in how you build your state. And in an event-sourced world like we have here, that end state is the snapshots that are getting rolled up and stored in the snapshot store. We try to make sure that all of the state is additive only. It can either mean that it is literally additive, like we're taking two integers and event A says add on 5 and event B says add on 4. We're going to end up in 9 no matter which order we process them in. Some state changes, some events aren't as obvious as that, but we can still try to design it with a monotonic state change. Make sure that the state always has only a unidirectional way to end up in a particular point. If a reservation that we have early on when the customer places an order eventually gets shipped, and we have two events for that, place the reservation and ship the order, it shouldn't matter what order in which we process them, because a reservation once shipped can never return back to the just created stage. So if we process the order shipped event first, it doesn't matter. We should still keep that marked as shipped, even if we later process a create reservation. Other bugs. Downstream consumers, maybe caches of our information, may have their own bugs, or they may have data loss. Maybe their system goes down. What we can do in that case is replay ourselves. Either they can pick up from whatever's in Kafka if it's being read asynchronously and they've only lost maybe the last day's worth. But if they need a full replay back from the beginning of time or from weeks ago, we can replay ourselves from our own data store's change feed. We may have random restarts of compute. In this model, that works fine. All of the compute is stateless. If it comes down, maybe some partitions won't be processed for a few seconds until it gets rebalanced, but we should still end up okay. We might have a total loss of the Kafka cluster. That might sound familiar if you think back to the beginning of the presentation. And we'll talk about techniques we can solve with that, or how we can solve that problem in a moment when we talk about how we actually did solve that problem. And we might have problems as catastrophic as an entire region going down. Now we can solve that by running hot where applicable. Or we can, when we're using Cosmos DB, we can switch the right regions for the data store in seconds. And if we don't want to be hot for a particular system, maybe for cost reasons, we can still scale up a secondary region of compute in seconds with modern techniques like using Docker and some kind of service like Nomad or Kubernetes to schedule on a new cluster. We found that another benefit of this model is that it's really easy to add features. Here we have a feature called the merchant snapshot expiration. Just because a merchant has told us that they have 20 units of something 3 months ago doesn't mean that we should still believe them. They might have sold that off. Maybe they're just not very accurate for whatever reason. So we decided to introduce a service that after a certain amount of time will delete that snapshot. We'll just zero it out because we don't believe them anymore. And we found that when we implemented it, it was really good business win for us. It dropped our reject rates pretty quickly. Now this entire service or a set of services was developed by a single engineer with light F# training and no cloud microservice background before this. It went from design to production in 3 weeks. It's because this system, in order to develop this additional feature, we were able to just add on to what was already there with very few changes and easy to test that everything worked out okay. One of my favorite benefits from event sourcing is that it gives us a time machine. What I actually mean by that is that with the stream of events, we can see the state at any point in time. We can walk step by step through everything that happened. This is great for troubleshooting. This is great for when a customer comes to us or a merchant comes to us, says they thought they were putting changes into the site, they're uploading them, but they never see anything. Or maybe they put it in and it's there and then it disappears 5 days later. They have no idea where it went. With a time machine like this, we can validate the behaviors that people are observing. If people report the problem around a specific time, we can go back in time and then re-observe it and do a root cause analysis. You can do this days, weeks, months later. Having this event stream, be able to go back in time to any given point is fabulous for troubleshooting, for auditing, for analytics, so many things. This model scales really well. In practice at Jet, we deploy all of our compute and schedule on Nomad clusters. You don't have to use Nomad. A lot of other ones are popular, but that's worked well for us. All of our compute is then independently deployable, independently scalable. Our data store is then scalable within seconds as well, since we use Cosmos. And not just scalable in terms of throughput, but in terms of size. There's now automatic splitting in Cosmos so that if partitions get too full, if there's too much storage being used, it will continue to grow on its own over time. In practice, this has worked really well for us. Overnight, we went to 250% of our normal throughput when a particular merchant started dumping way more information than we needed. For the most part, just repeats of data that they had already sent us. And while we do have some filtering on the API side, a lot of it did still get through to this degree. It wasn't a big deal for us. We saw that it was happening. We scaled it up to 250% to deal with the flow until the merchant was able to fix it. When that was done, we just scaled it back down within seconds. No problem. The last benefit I want to talk about with this is how testable this model is. 100% of the domain logic in Panther is unit testable. When you execute the state of, or execute a command against the state and you produce an event, that entire piece of logic has no external dependencies. When you apply a new event to an old state to produce a new state, you have no external dependencies. You can identify every single path through the business code and test every single one. Not just write unit tests, but you can write executable specifications with whatever invariants need to be checked with large numbers of randomized inputs extremely quickly. There are a lot of tools out there that can help you with that. One of our favorites is fscheck. All you need to do is say that inventory should never be able to drop below 0 no matter what events you add onto this state. And it will be able to test that and make sure that no matter what combination, that continues to be true. If not, it'll tell you. That is a huge win in being able to write new domain logic quickly and get it into production, knowing that you have all your bases covered. So let's go back to the story I was talking about at the beginning, where we had our Kafka outage. How did we actually deal with that? It ended up being no big deal. We got all the teams online, who are especially the ones who are at the edge of the company, exposed to the outside world. All of our merchant API inputs, all of our customer order inputs, anything that touches the real world. While we were doing that, we rebuilt our Kafka cluster. Just set it up in a new location, completely fresh, had no data in it, but getting it ready to go so we could replace the old one. We scaled up all of the systems to be ready for this by an order of magnitude or more. And then once all of that prep work was done, each team reset the checkpoints on their event streams to a point prior to the outage. It caused all of those systems to just re-emit all of their events to the downstream consumers, who just reprocessed it again with no problems. And because we were scaled up so far, we were able to catch up very quickly and get back to where we were, and with no loss in any data at that point whatsoever. This was a huge win for us in establishing not only that all of our processes worked, but all of our design principles worked really well in order to deal with the kind of scale that we needed at Walmart. So going forward, what are we going to be doing? Jet.com is now a part of Walmart. Walmart and Jet.com working together to unify our back-end systems. But in the meantime, we still have to deal with the fact that all of Walmart's servers and all of their systems exist in data centers, where all of Jet's are up in Azure in the cloud. So we're moving forward with a hybrid cloud approach. We have services in each side that connect through ExpressRoute, just like the systems are talking to each other in the same data center. It's proved to be a very scalable model. We've added some new data centers that are close geographically to the data centers that Walmart has physically, and we're able to keep latencies really low for all the communication between them. Now, once we have that in place, we'll be able to move data and systems into the cloud gradually. We're identifying all of the points where the systems interact. A lot of these are in Kafka, a lot of these are HTTP, but we find where those integration points are. Now, because we follow the asynchronous event model, and we're able to read events from the same stream with new systems, piece by piece, introduce a new microservice that is reading from the same stream as an existing service, and confirm that in parallel that they're working. If appropriate, we can do some A/B testing or canary testing, where we slowly start to migrate traffic over from one piece of that interface to the other. If the interface is more complex and there are more integration points, we can still do that gradually. If there isn't a good integration point already in place, we introduce a strangler pattern where we set up an explicit interface and are able to, over time, gradually migrate features from the old system to the new system. The goal here is to eventually get a significant portion of Walmart systems running in Azure, so we get all of that scalability while still taking advantage of all of the data center resources we already have in place. We found that functional programming has been a huge boon in helping us write code quickly and get it to production without any problems. And it turns out we've been very happy with all of the principles that we've adopted originally and hope to continue using them for years to come. Two books that I found very useful and recommend that everyone on teams that either I join or when people join teams that I'm on are Designing Data-Intensive Applications by Martin Kleppman and Domain Modeling Made Functional by Scott Woloshin. The first one is 600 or 700 pages of in-depth but very readable analysis of how to build systems that run at scale, that meet all of these principles of consistency that I've talked about, and help you understand what works and what doesn't, where the problems can come in and how to avoid them. The second one talks a lot about using a lot of the techniques that are in F# and other functional languages to build the kinds of domain models that I talked about earlier, where the domain is very explicitly matched to, or the domain code very explicitly matches your business domain without a lot of the problems, a lot of the runtime errors that you might get in other places.
Scott, do you have my mic back on? Hello, can I have my mic back on? Wow, that was amazing. Hey, let's give it up. So we have some time for some Q&A. I'm going to start with a few, but please line up at the mics. We'll have some questions. Boy, this is fascinating stuff. You know, you talked about resiliency. The way I like to define resiliency is robustness in the face of change. And in physics, we once professor once described this as, if you had a cereal bowl and a marble in it, there's two ways to configure it. One this way, and you can bash it, and the marble rolls around and always ends up the other way, at the bottom. The other is to take that cereal bowl and move it this way and put the marble on top. And then, as long as nothing changes, it can stay that way. But the least perturbation of the system, it never returns to the normal state. And so what I like so much about your talk was, it seems to me that you've got a very robust system because you have managed your state very, very well. So I had a couple questions about that.
Sure.
First is, I followed a lot of it, but not all of it. Do you have a white paper that describes this in more detail?
I suspect that we do, but I don't have a link for it right now. We have some blog posts, I know at the very least, that go in more detail.
Fantastic.
I can find some links for those.
That'd be great. And then, can you talk about the, to what degree do you get this great state management through functional programming versus, say, if you used Azure Functions? Would you get the same sort of thing with Azure Functions?
Azure Functions have, I have a lot of hope that they will develop into what I would like to see our microservices being. The idea with Azure Functions is very similar, that they get the input message, they run some kind of function, have some kind of output. It's very much like our microservice model. The biggest concerns I have with Azure Functions right now are how quickly they can scale up and what kinds of latencies you're dealing with. When you're talking 3, 4, 5 milliseconds latency as your desired or as your requirement, that's the biggest area where they don't quite meet the bar yet. But I have huge hope that stateless computing, like with Azure Functions, over time will get to that point and be able to replace this entire infrastructure.
Got it, yep. And then you mentioned that the messages were idempotent, but I didn't follow that. How are they idempotent? Like, say you say update a inventory, is that like -2, because somebody ordered 2? How's that idempotent? Is it through the ID itself?
Yeah, there are a couple of different ways that we achieve idempotency. One, if it's an update inventory event or command, because in this case they're nearly interchangeable, it's not adjusting the inventory up by 2 or down by 2. It is just saying, this is the state right now. We have 2 in the warehouse. So as many times as you tell me that you have 2, you still have 2. Now, for the Some of the others do involve delta events, like the reservations, where maybe we need to set aside 2 for this particular user. And that is part of the state that we need to store. We fold over that state to make a reservation to say that this particular customer has ordered 2 of this particular item from this particular warehouse, and that is now on order but not yet shipped. If we get another reserve inventory in for that same customer, it'll have the same order ID, which itself is enough to help, but the same order ID, the same item ID, the same quantity from the same warehouse, it matches up with the state that we already have. There is no potential delta against the current state, and that makes that particular item potent.
I see. I think I followed that. Okay, very cool. Okay, I got 2 more questions, so you guys should line up if you have some. The first was, in this functional programming model, and you have such well-managed state, it seems to me that that would make it easy to roll out updates to your application. Is that the case?
It really is. The versioning is, it turns out in practice, has not been nearly as hard as a lot of people are often worried about, and as much as we've been worried about. When we want to make a new version of an event, we just make a new event that's v2. We make the changes to our command processor code to support it. We make changes to our snapshot event stream to support it. And then we just roll out those changes, replacing in place the existing code. And then once we just make sure that that's there before the new version of the messages come through. It works really well. The problem with it is that if you maintain the same code base over years and years, you may end up having code that needs to handle not just the latest version of an event, but maybe you're on version 20 and they're 19, 18, 17. In practice, we've found that that's not a big deal. Maybe that's just because we're a young company and haven't had 3 decades of different events that we need to version. But at least when we're talking on a few year period, it's very easy to just write the code that supports a new version, deploy it, then let the new version come through, and everything works.
All right, let's go here for a question.
Talking about the time machine, you were mostly talking about replaying the past. Are there also things where for like forecasting and maybe looking at what you're ordering or what styles are for like an upcoming season or something where you have to predict the future with this stuff too and do different things using the same kind of models?
Yeah, the models end up being different, but the historical data ends up being critical for that. While talking about order forecasting, it's a little bit far away from the domain in which I do have experience, but one that is very similar is using the historical data to predict how accurate the incoming inputs are. We may have, and we do have, some merchants that maybe they tell us they have 10, so we try to send them 10 orders, and 2 of them get rejected. And maybe this happens a lot. We can use this historical data, and this is something that we're actually rolling out in a couple of weeks. Machine learning models that are taking all of this historical data, analyzing to say, hey, we're getting rejections for these reasons over 250 different variables. Maybe this merchant dealing with this particular kind of item, they're just really bad at it. And we then adjust how much inventory we think they have. If they tell us 10 and they're always lying and reject 2, we adjust the number down to 8 pretty quickly.
You mentioned generative testing. Have you been able to leverage that to do end-to-end integration tests to provide, like, look at your SLAs and say we're actually providing these SLAs and consistency guarantees we project?
We can't do that within the domain because the domain is entirely without any external dependencies, and that is where we're doing most of our generative testing right now using FSCheck. We have started looking into TLA Plus to do full end-to-end system testing of similar specifications, but that's not something that we've actually gotten to do yet. It's just something we're still exploring, but something we absolutely want to do and is on our radar.
You mentioned earlier about event stream. Assuming you will have thousands SKUs and hundreds of warehouse locations, right? Are you maintaining this combination of these event streams? For example, tissue at house in California or New Jersey, each one will have its own stream.
Right. That's one of the things that we changed from our original design. Instead of having all warehouses in one stream for a given item, we've split it into each item at a warehouse has its own stream. Yep.
So when the customer order, so is that you designate a specific location with the order, you have to attach that location property to that stream. That's when you check against it. So basically like thousands of queues in that sense.
Mm-hmm. Yeah, I didn't talk about this a lot, but one of the things that makes Jet.com different from a lot of the competition is its pricing engine, which adjusts prices for the items in its basket depending on what else is in the basket and if they can all be sourced from the same location. What that means as a consequence is that by the time you check out, we already know from where it's going to be sourced, which warehouse. And so we can make the reservation at that point against the particular item at a particular warehouse. Now, not all front ends, not all sourcing engines work that way. Walmart.com is migrating toward that, but doesn't have that yet. I do have an architectural diagram that's a lot more complicated for what we're doing next generation, where we can make reservations at the item level, regardless of the warehouse where it might eventually end up being sourced, and then migrating those reservations to more specific subsystems as we get more specific sourcing information.
I see. Another question you mentioned, when you have your cluster fell down, you were able to, don't lose any data. To me, they will have, different streams and different timestamps, right? So could you explain a little bit more how can you don't lose any data?
Yeah, well, Kafka might have gone down, and everything that was in flight went down. Every system that put a message into Kafka in the first place still had all of its data, all of its events that it was writing into Kafka. So all we needed to do was make sure that once we brought up the new cluster, that any event that was writing into Kafka, or sorry, any system writing into Kafka did a replay from a point in time that was prior to the Kafka cluster going down.
I have a question about that as well.
Yeah.
In your diagram, you showed the commands coming in. Mm-hmm. Is there a store for the commands before they get to the command processors to replay?
Generally, no.
Oh.
We haven't found value in storing both the commands and the events, usually because any domain command for a system maps to events that are coming from an upstream system. Mm-hmm. For instance, in this architectural diagram, where on the lower part, where we have all of our inputs, inventory and order updates, that get put into commands that are in Kafka. We have a stateless mapper that maps the message to a command. But upstream, an order update comes from our order processing system. That order processing system already has its events that it can replay. So all it needs to do is replay those order events. They will get mapped using our stateless mappers into commands again, where we can then reprocess them. In other words, we don't need to store the commands because other systems already have the events, and we can just convert them.
Thanks.
Thanks for the talk. So I have two questions. The first one is regarding regulatory compliance based on the region. So you said that it's possible for you to have like two versions of a process command, right? What happens when you have to have like versions that they need to live together? Because, for example, like you need to comply to something in China.
I'm sorry, can you?
Yes.
The last part? Yep.
Yeah. So my question is like, how do you handle having not just like a version of like a command, but like the equivalent with like a small difference? I'm thinking of like now with all this regulation that we are seeing, like it's very nice to have the cloud to say like, yeah, the data is going to be stored just on the London data center. That's very good, right? But when it comes to the business logic, do you have like any insight how can you keep sanity there when you need to change the logic?
Yeah, we probably won't need to do a lot with that directly in how we design or write the code. When we're keeping when you're having to keep the data separate in the first place for the regulatory reasons, we probably aren't going to be shipping inventory across those regions that have the different regulatory domains either. It's not something we've had to do so far, and that has been sufficient so far. Okay. Maybe we'll have to revisit that in the future, but it's not a problem we've had to solve directly yet. In other words, or to expand on that a little bit more, if we were to expand into those areas, we'd probably just roll out a new version of the system in that particular region to deal with the inventory and whatever business problems we have in that particular area.
Okay. And you think like if you go that way, right? If you have to have like a command for like, update the inventory, right? And they have like a different set of like, basically it has to be processing a different way, but semantically it's the same. Like, do you see that this will be like version 2.1 of the same, or like, like something different? Like I'm thinking like, how is this going to look like 5 years? Because this is like an ongoing process. Like, and e-commerce is not something that you can stop and say like, this is like version 2. Mm-hmm.
Yeah, we decide to version when the data formats that are coming in don't match anymore, and the semantics don't match anymore. If we can do a map from version 1 to version 2 statelessly and not lose anything, then that's what we'll do. But if the semantics change, and if the semantics are different between one version and another version, then we do have to treat them separately, have a different code path. We'll still maintain the old code path for the old versions or the original versions, but we will have a different code path at that point.
So if I understand that right, you are saying that the signature of like a command to be processed is something more than a string. It's like the data, it's like where it's coming from, it's like more rich, right?
It's more than just the shape of it. It's definitely what the intent is. That's the point behind a command, is that it is expressing an intent to do something. Okay. So if that something that is intended to be done changes, then that's a different command, even if the shape is exactly the same.
Okay. So my second question. So you were saying that you are using microservice and you are looking at the functions, right? So if I look at the service and the functions, this is just like ways to deploy business logic, like, right? It's just like how you deploy like new code and keep it like there until it's safe to run, right? Do you have like a wish list or like, besides the latency that you mentioned? Because right now, functions, F# functions, it's just it's a .NET component. It's just a .NET and you run it there, right? But the thing is like, there is like more than one ways to run that, depending on the interpretation of the container. Like, for example, like if you run an OGS functions, right, on Google Cloud, all the code that is outside of the exports, that is persisted there. So if you have a LED and you increase that, the next time you call the function that is there. So this is not going to happen with F#, but my point is like, besides the latency, is there something else that you would like to see on the F# functions on Azure, so that it's easy for you to say, you know what, let's remove all the hassle with the microservices. Let's go completely functional here.
That is a good question, and I have not looked into functions enough recently to do a full evaluation. I kind of, just for time reasons, I got to the point like, oh, this is not good enough. Okay, yeah. I'm not going to worry about it until this gets solved, and then I'll look at the rest of it. So maybe there's more. I don't know. Sorry.
Okay. So I guess since you are on a stand, and do you feel like the knowledge of like what the community is asking for functions that is like there, like that? Does Microsoft has a very good idea of what the community is expecting with functions? Because right now it's like we are like opening like a new door, and we we need to deal with, like
Yeah.
how to keep
Gotcha.
like versioning on this, like how to keep the correctness.
I think that with respect to functions, it's a different way of thinking about the world, and it'll take a while for people to get their head through that and then to understand both its benefits and then what things they need out of it. In my mind, I liken it to, when we wrote, console applications, right? You have a main and you have an exit, and you just walk through it. And then when we started doing Windows programming, we had a message pump. And all of a sudden we had to learn, like, wait, what? So I write, what? I wrote this event handler, like, how's that call? Like, where do I call my event handler? Like, no, somebody else is doing that. And the state management associated with that, and how you build applications. And if you recall, it took a long time for people to get their head through that. And then once you got your head through that knothole, that's the way I view this model of, there's this knothole. There's the world on this side of the knothole, and there's the world on that side of the knothole. And you got to get through the knothole before you understand this world. I think a lot of people are on this side of the functions knothole. So.
Thank you.
Okay, we've got time for a couple more questions. All right.
Within your F# code, are you using, for example, like the reactive extensions to sort of, with like a functional reactive model to handle the, like for example, mapping from the commands to the events, or sort of how do you handle that within that infrastructure? Do you use pre-existing F# infrastructure like workflows or something like that to handle that?
Yeah, we did a lot of experimenting with some different models as we were getting started. There was a big internal political battle about the push models of reactive extensions versus the pull models that we get from a lot of queuing systems that we were using and are using now. I don't think we are using RX anymore anywhere. We've gone from the observable model to the queue or the asynchronous queue model, where we have an arbitrary number of messages, and then that exist in a queue, and then as the worker is free, it pulls some batch of messages off that queue, operates on them, and does whatever side effect it needs.
Is that more of like an Akka.NET style?
It is. We try to write it, and I feel like I'm repeating myself on this part, in a functional style, where the entire process, where once you have the immutable message and your immutable state, then it's just a pipeline of functions that you pass this through. That is mostly domain logic or general microservice logic. Then what makes each microservice different, is the way that or the harness that you put it in. How do the messages get into that pipeline, and how do the outputs get written out of that pipeline?
Okay, thank you.
Yep, thank you.
Last question.
Hey, apologies if you explained this. The example you gave with the baseball, where there was one last one left and you've got the two data centers running east and west. Do you only have a single stream? How are you managing that, like in a millisecond, that there's only one person can buy that last baseball? Are you running, like, is there just one stream across those two centers, or how's that being managed?
We're hoping to do something with a multi-master model where you can do writes to any region, whatever the closest region is, and turns out there just isn't a way to get around or to deal with that problem. So all of our reads, we have the data stores replicated to whatever regions are closest to the customer or closest to the data center that's being hit by this. But all writes still go to a single data center, a single stream. So you can read the single stream from any region, but the writes all have to go through a linearized writer.
Gotcha.
Yep.
Great. Hey, let's give it up for Scott. It's a fantastic session. Thanks so much.
Thank you so much, Jeffrey. Appreciate it.
Have a great build.